Okay, thank you. First, I would like to thank the organizers for the opportunity they gave me to talk here, and more importantly, I think, because here it is personal, I think I would like to thank them for all the organization of the workshop. I think it was wonderful and really well organized, so I think we should applaud them for this. And then I'm going to talk about some stuff, which is the title here, actually, in joint work with Denis Perrault. So you can view really this talk as the very sequel of the one which he has done Tuesday. There will be maybe some repetitions, so some things that each may be good. So I hope it will not be too much boring. So let me begin with some motivation about the problem here, in which we are dealing with. So the motivation for this work was, at the beginning, the transverse index problem of Connes and Moscovici. So you want to understand the transverse index theory of foliations. And then you want to find a sort of K-cycle which takes into account the transverse geometry of the foliation. So I will recall briefly the setting about this. So you begin with foliation ZF. So let me draw something here like this. And then what they did first was to reduce through a Morita equivalence to some study of a cross product with a group of diffeomorphisms. So something like this, or let's say W. You have gamma, which is a group of diffeomorphisms of W, and the gamma here kind of encodes the holomonomy of the foliation. So, for example, let's take a W here. And then you want to study that thing here at first. When you have a great problem which arises here, because you cannot do actually good index theory with that kind of object, because you cannot find any elliptic operators on W which is gamma invariant in general. So, and this, it is even at the level of the principal symbol. So you cannot doing index theory in that kind of setting is not really defined. So no gamma invariant elliptic operator. This is because you have no Riemannian geometry which is invariant under that type of thing here. So the idea is to pass through a Thom isomorphism through the bundle of Riemannian metrics. So things like this. So here we have Riemannian metrics. And then what they have succeed in that setting here. So here you have W, you have P. And what they succeed here was to construct a hypoelliptic signature operator on which you can really do index theory on. So they constructed some hypoelliptic signature operator which is something like a Q, which is equal to a leafwise signature operator here. So let's gamma V, for example, plus a horizontal one in that direction. Let's say delta H. So you have horizontal here, vertical here. And then this operator is not really gamma invariant under the action of the group. The group is you can lift the action of the group here to the bundle. And this is not quite gamma invariant in total, but just at the level of the principal symbol it is. So you can redo index theory now from here. And that was the purpose of introducing spectral triples from there, because their theorem was the following. You have that this algebra here. So cross product of gamma. You have a L2 of something which is morally takes into account that decomposition, that foliation. So an L2 of something, and a D which is related to Q of Dirac type, such that here you have a regular spectral triple. Then you all know here, I think, that once you have a spectral triple, index theory amounts to just calculating the Chern character of that thing. So then you all know also that using residues, you have a formula for that thing. But here you have a new problem which appears because this is not computable, at least difficult. So once you are here, you want to find, here you have a formula which is kind of abstract because you have a residue of zeta functions. And what you want to do is having a characteristic class formula, actually. So goal is having a characteristic class formula. Then what I did on that for that purpose was to introduce some Hopf algebras and the cyclic cohomology which is affiliated to it. So they constructed a Hopf algebra in order to reorganize all the calculations in order to make it computable, define their cyclic cohomology. So let's say Hn. And they constructed a map called, let's call it theta, which goes into the periodic cyclic cohomology of that thing here. So I hope you can see here. Okay. The good thing about here is that good news. You have good news here because that thing is a really geometric object. So you can show, they show in their paper that it is a theorem of Connes and Moscovici, which is here the Gelfand-Fuchs classes of the manifold. So if you don't know what it is here, roughly speaking, it is just some characteristic class. The algebra here is just generated by the Chern classes, and you have some differential you can do. And there you have really the characteristic classes. So here you have Gelfand-Fuchs. And the other theorem they had was the following, Connes and Moscovici, which says that the Chern character here, so the Chern character is here, the Chern character belongs to the image of the application here. So what you have done is to transfer a sort of kind of analytic formula here to a geometric formula. Another question now is, what is this class? So And then they kind of show that you must have in the preimage of theta some polynomial in the Pontryagin classes. And now the purpose of that work is to see it from on a completely different point of view. Not completely, but a very different point of view. And this is the purpose of my talk for now. Just one thing. Here, the hypoelliptic thing, this uses the Heisenberg calculus on foliations. So I'm going to record it before starting really the talk. And oh, it's very heavy actually. Okay. So let's do some, we will record some little things on this. So you start from another foliation, which is not the one of the ZF, which is more about that vibration in the role of what you want to do. Let's call it MV, foliation. And then I'm not going to detail in detail. I'm not going to give in detail all the things about Heisenberg pseudo-differential calculus, but just gave the main idea of this. So locally, you have a decomposition like this. So some kind of RH, say, RV. Then you can decompose locally your manifold like this. So the purpose of the Heisenberg calculus is just to say that when you are in a horizontal direction, a transverse direction of the foliation, you have order 2. So this is a weird thing here, but vector fields here have order 2 as differential operators. But in the vertical direction, this is still the same, order 1. But let's see on one example what is the interest of doing things like this. Let us define the operator, which is a sort of sub-Laplacian, the following one, which is dx1 to the power 4 plus etc. plus dxn dxh. So v is the dimension of the foliation, h the codimension, etc. minus dx v plus 1 square. Here is the thing, plus dx n square. And then let's say that you look at the usual principal symbol of that thing. So principal symbol is what? Let's see. Higher order terms are here. So you have something like C1 to the power 4 plus etc. plus CV to the power 4. This is not elliptic. But let's say now that you have that kind of order. Now this means that here you have order 4 because this counts 2. So it is like let's call it H symbol, H principal symbol. This is really the same thing. Plus you can take into account the rest. So plus this plus Cn square. And here you have a full principal symbol, and here you have something which is kind of elliptic. This thing is non-zero only if you have a Xi which is non-zero for all the coordinates. So this is the main interest of that kind of calculus. And actually, even if I didn't define it properly, that operator here, the Q, has that principal symbol here. So now you can do index theory in that kind of sense. And now let's look at another general setting. So now you want to have a group of diffeomorphisms which acts on M leafwise. So you respect all the leaf on all the foliations. Leafwise action. And then let's forget for the moment about the group, just for now. And then let us see about what happens. So that's here, there is some repetition with the talk of Tuesday. So what you have here, you have something very similar to the classical case, the non-foliated one. You look at a pseudo-differential extension, or exact sequence if you want. So you look at something like that. You have regularizing operators on M. I don't denote M because this is kind of obvious here. You have then the symbols of order 0 in the Heisenberg sense. So taking into account it's this kind of order for the symbols. And finally, you have the full symbol, which is the quotient. SH0, and you finished that one. So now here is the approach of what we are doing. As you have a short exact sequence in cohomology, you can extend it to a long exact sequence. For example, in K-theory. So in K-theory, if you work with the algebraic one, it is just the K1 to the K0, but it is okay for us. So you go to the K1 of that thing to the K0 of that thing here. And you can also do the same downstairs. In cyclic theory. So you can go to the cyclic homology of that thing to the cyclic homology of that thing here. So this is by Kunz-Quidden theorems. So you go to cyclic the periodic one of that thing here to that thing here. Oh, HP0 of minus 1 infinity. You can do the same in cohomology. So here HP0, HP1. And you have arrows which relates both here, which is the Chern character, the odd one, and here the Chern character, the even one. And then the theorem of Nestor was to show that here you have a commutative diagram. So it was then having a commutative diagram, what we can do is the following. Here you have an obvious trace because you have regularizing operators. And you can take its class. And then here, an elliptic symbol here gives rise to something which is here invertible. So you can take its class in the K1. So it is, let's take a symbol U here. And what you have by this theorem is the following equality, which says that you have something, a pairing, an equality of pairings, trace of, you follow the diagram. Here it is the index map. Here let us denote that boundary map by D. And you have that trace evaluated in the index of U is precisely the same thing as going the other way around. So here you have the d of the trace of u. What you can think about, if you, as you know about K-theory, is that here you have obviously a sort of analytic index which appears. If analytically you have you don't have any problem, for example, the foliation is compact, and etc., here you have a Fredholm index. So here it is an analytic index. And here, it is what should be thought at as a topological index. And one thing you can prove actually now is the following proposition, say, which says that this thing is calculated as the following cocycle. And here we can recognize the thing which appeared in Sylvius' talk, which is the Wojcicki residue of that thing here. The delta is the operator here. And there is a 1/4. So you have that theorem here, and a local index formula in the sense of Connes and Moscovici here. And actually, I let some space here, and this is no more deal than adding the action of the group. So you can add a cross product here. The interest is that you have you don't have any more pseudo-differential operators here, but something more general. And you can still do index theory updates in that sense. So the approach here is kind of cool if you want. So you have some things to modify here. You have to localize the trace at the identity. And here, the Wojcicki residue, you have to modify it to go to the identity. Here, the Wojcicki residue is kind of modified because you have that filtration here, which is not the same. So the integral of symbol sigma is something like an integral over a certain modified cosphere bundle, which takes that order into account. And you take the integral of the symbol up to a finite order. So here, this is V for the dimensions of the leaves, plus 2H. The 2 is the order you put in the transverse vector fields, and the H is precisely the codimension. And you integrate with respect to something. This is not very relevant for us for now. Then what you have done here is something which is quite relevant because you just reduced a sort of topological problem here to something which is purely algebraic. Here you have a star product of the symbols, and then the game is now to find the order of that thing here. So here is the game, and this is the difficult part, actually. So I will sketch some ideas to find something which goes into there, directed in that order. But I also apologize because I will be a little vague. So I begin with a very vague idea. Still one more thing. Before going into this, one last thing is that actually your thing here can be related to the chunk character of the thing here. So here you work at the level of a full symbol. Actually, you can reduce things to the principal symbol in the Heisenberg case. This is not very difficult. And at the level of the principal symbol, you will be in some algebra of the type C infinity of the cosphere bundle crossed with gamma. Okay? And then you have a map here, rho, which goes from the cross product of that thing here, not that thing, C infinity of M, cross product with gamma. And the rho here is just some kind of Toeplitz operator. So rho is just PAP modulo operators of order -1. The P here is the spectral projection associated to the Q, for example. So P is equal to 1 plus Q, Q-1, roughly speaking, over 2. And one other proposition you can have from here is the following. So now, okay. Let's say proposition or theorem if you want. The Chern character of the thing which is hidden now is equal precisely to the pullback of that cocycle here. So you have a rho star times d or the trace. So we have that thing. So actually, now you have a kind of other local index formula, but directly on the operators here. If you look at the entries here, you have operators or their symbol. Here, you are working at the level of the algebra, actually. So now, as we were saying, the game is to have something which is exactly of order minus v plus 2h in order to compute the thing. So let's begin with this very vague idea. Is the following. If you know about cyclic cohomology, so you know that cyclic, the cyclic cocycles, the model cyclic cocycle. Is something like A0, dA1, etc., dAn integrated over something like this. Okay, so let's say it is not a m, let's say a z. In the commutative case, this amounts to this. So it is a theorem cycle. So let's put it around, but now here's the game. An observation is that here you have a symbol of order 0 now. The integral is over something. Let's don't detail for the moment. But if you do what? dA1, you will decrease the order. dAn also. And as you have an algebra of pseudo-differential operators, you will have here something which is of lower order than before. So now the game, the goal of the game here now is to create to construct some homotopy between the cocycle here and some cocycle of that type, which is of higher degree. And actually, there is a recipe about this to perform some such homotopies. So the recipe is about J-Lo formulas or cocycles. So let's just sketch what we need about to have these J-Lo formulas. I don't write the formula because I don't think it will be more relevant for the talk. So, but at least what we need is the following. In the classical case, this is really like a spectral triple, but you want to make sense of the Hill kernel. So you have an algebra A, which is represented on a certain Hilbert space H as operators. This is one point. What you want to have is a sort of heat kernel. So a sort of exponential of minus t, something like this. And so you need also implicitly a Laplacian. You also need a sort of square root of the Laplacian. So a sort of Dirac operator. Here, Dirac type means that if you take the commutator with someone in the algebra here, you have a sort of differential. And lastly, what you have to make is taking the trace, and as you want to take the trace, you have some analytic issues about summability of other things. So the trace, and this implies also summability conditions. Which means analysis. There, you can do something else. So what we want to do is to perform that kind of setting to here. So the algebra A is no more the algebra of functions, not the usual one, but we work at a higher level. Here the A is like your algebra of symbols. The H is replaced by something which is not a Hilbert space, which is also some kind of operators on symbols. So to do that thing, you just have to see the algebra of symbols here. So SH is simply viewed as a bimodule over itself. Why to do this? To explain the reason here, actually you can have all the operators we need like this on symbols, because if you do the commutator with xi, you know that this is the derivative with respect to the covector xci, and if you do the commutator of xi with that thing, something, a symbol, you take the derivative with respect to xi. So actually you have all the operations you need on symbols derivatives. So here is the main idea. There is some detail which is quite involved, but this is really the main thing. Then you have this can be construct, but this is quite involved actually. Laplacian plus that thing, possible. Look at, for example, the example of Rn, which we see as the foliation down upstairs. So if you have Rn, let's say you have an operator, which is f, which is like the sum over xi dxi plus xi dxi. Okay? So here, what you do is, if you do the f square, fa, you have I, the complex of the square root of -1, dA. And just by remarking this, if you do the f square, you have the symplectic form on the cotangent bundle. And here is the flat case, actually. And The difficulty is to globalize that type of calculations here because you cannot make sense of xi globally. So, but this is possible. You will have some, in the global case, oh, I have no more colors. So, okay. In the global case, you will have a sort of operator D, which is such that you will have the commutator of D with A, which is dA, but up to something. Here, you can remark that you don't have any symbol left. So that thing is like a constant in your symbols algebra. And it commutes with everyone. So here, you have a central element. But here, the funny thing is that when you perform the construction, all the construction here globalized to that thing here, the commutator with the Laplacian will hold some curvature terms. And this calculation will lead to the following, so theorem. So once you have that formalism here, it is easy to construct a homotopy because you just have to fix two Dirac operators which are kind of different. So here a D and a modified D. Here, what you can do is the same. For a good choice of D, what you have is that calculating this will be equal to phi of the third class, the equivariant third class. I will define this with the first board. So here is the equivariant third class. Then let's see on the first board. I had a diagram, but okay, it's here. So now let's see what happens here. What we have done is just working at the usual cohomology. So you have here the equivalent cohomology. E gamma is the universal bundle over the universal gamma bundle. And then here you have the homotopy quotient. Actually, for us, we are at the level of sphere bundle, but it is not very important for here. And what we can do is here to construct here a map phi, which goes to the equivalent cohomology, to the cyclic cohomology. So it was constructed by Connes in 1983, I think. And actually, you also have a map from here, which is due to Bott, and which is just some Chern-Weil construction. And then you have the theorem of before. That one here. So now I think it's maybe time to stop, or how many time left? Oh?
You have a bit more time.
Oh, okay. So, I didn't predict that. So doing this, maybe I'm going to give some more details about this. Just the formulas which are involved in the flat case, so that you understand where the third class appear. So what you can do, where should I begin? let's say there. So what we will have actually, the best thing to is the following. So let's say, okay, one way to look at the J-Lo formula is the point of view of Quillen, which says briefly that you can obtain the J-Lo cocycle as just a good trace of some curvature, but not in the sense of geometry, but in the sense of a sort of more algebraic thing. So J-Lo, you can obtain it by taking the trace of some exponential of some curvature. Here, curvature, for example, where is the flat case? Oh, it's not the wrong board. Okay, you had that operator. I would like to have the other board actually. So, okay, let's switch. Let's switch and erase. I have to. Here. And here you have your operator F here. So you want to see things like a trace of an exponential of a curvature. Here on the curvature you will have curvature is something which makes mention of the F square, which is central. And you will have something which makes mention because, remember here, you have a log. So it is not like in the usual J-Lo formula where you don't have anything, but you can adapt things very easily in the Quillen setting. You will have the log of delta to the power 1/4 with something like this. And then what you will have in expanding that kind of type of operator on symbols will be something like, if I remember, we will have a cocycle phi, which is not the same, so let's denote it by this. We have 2k plus 1, a0, a 2k plus 1 of something. We'll have a formula which is not very easy at first, so minus alternate sum of the Wojcicki residue of A0. Then you will have something like F A1. You will have also here, if you perform that type of thing, a delta of F, which is delta is the commutator with the log. Etc. and F A 2k plus 1. Plus something like this, which is another sum of the same type, which is something like this. A0. And here, just the delta F replaces the F AI at the ith position. Then you have here A0 of the same thing. But here we will have a delta of AI, and then an F of A2k plus 1. And then you can just calculate the things here. So here you have F of A1, which is dA. Delta of F will give something which is a sort of dual of, you have the co-sphere bundle like this. And when you want to integrate with respect to the symplectic form at the beginning, so in the residue you have, the cotangent bundle has a symplectic structure, so you have a symplectic form. You can extend it to a volume form, and then here you have the co-sphere bundle, and you can take the induced thing, vector field, which will induce you a measure on the co-sphere bundle. So you have vector field L, and that thing here, which be such that when you do this on this, it will be 1. So here you have that part will really give something like A0, dA1, dA2k plus 1. Okay? That thing here will vanish because of some problems of order, and then you will amount to something like, here it is always a flat case. So your cocycle here, you can just take k, which is the higher order. It is a -1 actually. So k equal to n, the dimension of the manifold, and then you have that thing here. It's exactly that thing. A0, dA1, dAn. When you are here, it is as we said before. Let's say you don't have any foliation, so it is more simple to say this. Here you have order 1, order -1, extra, order -1. So you directly have the symbol of right order of order -n, actually. So here, what you can do is just taking the principal symbol, the rest will vanish, and then you will have something like sigma of A0. Here it is a Heisenberg principal symbol. It works also for the Heisenberg case. The sigma A1, d sigma An. So this is how things happen in the flat case. So this is some calculations. And if you do things in the curved case, what you will have to add will be just the third class. Here it is the curved case. And here you have performed all the calculations purely algebraically, so that you don't have any analytic issues actually. So I think maybe I can stop now, I think, because I have nothing more to say. Actually, we don't. I want to come back to what? Okay, I think this is that board. That's why it is sometimes better to have slides, I think. Okay, so here I forgot to say something. Here you have some summability conditions to have, and in the classical case you have it, and you have a true heat kernel. But here, the thing is that things are purely algebraic. The trace here is constructed from the Wojcicki residue, actually. So up to a finite order, you will clear all the terms of lower order, and you can handle things for the heat kernel like this, actually. So you really have no analytic issues in this calculus. So you don't have to ensure of having a true kernel. It is a formal one, just taking that exponential of something like this. Here also it makes sense because you still have the Wojcicki residue. And here you will see that if you expand to higher order cocycles, it will vanish because you have a differential form of order. So here is the thing. You don't have to the most important thing, I think, to retain from this is that the calculations are purely algebraic. For you.